All right, welcome to episode number 14 of the Base-12 Book Club, where I'm promoting my book, Understanding Base-12 Math, How to Draw the Perfect Circle Using Dozenal Geometry, available on Amazon or through Amazon. So what I've done in the book is introduce you to a new geometric pattern. It's a Base-12 geometric pattern that can only be found on the Base-12 Cartesian plane. I explain the difference between Base-10 and Base-12. And I show you this geometric pattern which can be used to divide the circle perfectly into 360 degrees. So I've made a lot of videos going over what's in the book and explaining all that. And so in this video, I'm going to share with you a few things that I've discovered since publishing the book. And in this video, it's going to be about Pythagorean triplets. So it's about the geometry of the Pythagorean triplet and how it is connected to the geometry of the Base-12 dodecagon. So it's something I noticed. So first of all, Pythagorean triplet is a triangle where all three sides are integers. The most famous one that most of us are familiar with is the 3, 4, 5 triangle. So it relates to a squared plus b squared equals c squared. So 3 squared plus 4 squared equals 5 squared. 9 plus 16 equals 25. So that's the essence of a Pythagorean triplet. So here you can see I've written out a few in base 10. Where again, 5 squared plus 12 squared is going to equal 13 squared, and so on. And then I wrote out I just converted those numbers into their Base-12 equivalent. So at this point, it's just integers being converted into other integers. But one thing you notice right away is that you get this 1, 5, 1, 5, 1, 5, 5, all of the Pythagorean triplets, and not just these ones, but every one that I have encountered now, when I convert them from base 10 to base 12, end in a 1 or a 5. So that actually, and I just realized this you get like 15, 25, 35, 45. Those are 12s. This is the base 12 side. So your 12 looks like the 10. It's got 1 and a 0. So when you see 21, 31, 11, 21, that's also in groups of 12. So there's a 12ness in here that I wasn't aware of. And so now we have something that just sort of connects the 12 with this Pythagorean triplet idea. But what actually got me interested in exploring this in the first place was that I noticed that another aspect of the Pythagorean triplet is that it can be applied to the radius of a circle. So if the radius of a circle is 5, and here you can look here, so we have a 5, and you were on the Cartesian plane, so that's a point that's going to have the x is 5 and the y is 0, and the y is 5 and the x is 0. We also have the points 3 over 4 and up 3, or up 3 and over 4. These are also lattice points on the Cartesian plane. So a Pythagorean triplet gives rise to 12 lattice points that define the radius of a given circle. And when I first discovered that, I thought that was like the maximum amount that you would be able to have on the Cartesian plane, because you got this grid and you're trying to fit a circle on it. But then I realized not too long as you go through the list of Pythagorean triples, you get to ones where there's 2 Pythagorean triples, like 2 different combinations of numbers that will give you the same radius of the circle. So here's 65, and then we convert it, it's 55. And so that gives you have 12 and then another 8 points, because you already have the 1, so that when you have 2, like a pair, you get 20 lattice points on the Cartesian plane. And then as I found a long list, and I realized that you get to another sort of level of numbers. Like here we have, these are the Base-12 versions of some hypotenuses of Pythagorean triplets, and all of these radiuses of circles have 4 pairs of coordinates. So that gives you 36 lattice points that define the circle. And as you continue, you find another, you get 68 and then 132. You get larger numbers, and some of these numbers have a lot of pairs of numbers, like when they're squared, add up to the hypotenuse or the hypotenuse of a triangle or the radius of a circle. And then I discovered there's one in particular that had a lot of them, and I converted it into Base-12. And I got, this is it here, 5BAA21225. So when you have a radius of a circle like that, all of those Pythagorean triplets fit into that number, divided evenly, as well as a whole slew of smaller single triangles that just sort of just have one pair. But when you add all those up together, this particular circle as a radius has over 1,000 lattice points that define it on the Cartesian plane. So I thought that was all really interesting. And what led me to that in the first place, just remember that, was that you can do the same drawing of circles with the points that define the dodecagon that you've discovered in my book. So the very innermost dodecagon is defined by the point 1.1, then you go over 1 and up 0.7, so the coordinates 1 and 0.7. So you can draw these two circles, and then the dodecagon sort of fits in between them. So this 1.1 is also a radius of a circle that can be defined as a Pythagorean triplet, because as it goes up here, it actually intersects that point there. You go over 1 and up 0.5. So 1.1 squared is 1.21, and then 1 is 1 squared, and then 0.5 in base 12 is 0.2 squared. 0.5 times 0.5 is 0.5 squared equals 0.21. So you get the 1.21. So that Pythagorean triplet is actually this one here. It's the 5, 12, 13, but it's when you convert it to base 12 and then add a decimal place in there, 0.5, 1, and then 1.1. So there's the 1, 1.11, and 0.5. And so then I realized, yeah, a lot of these can grow. So this is connected, and this obviously, the next one, you go 1.1, 2.2, 3.3, 4.4, and so on. And so a lot of, there's threads of Pythagorean triplets that sort of go through the Cartesian plane, and I think there's sort of rings of them. It seems like there's certain rings, certain radiuses of circles that are going to have a lot of coordinates that give rise to like sort of thick bands of circles that are relevant. So the underlying belief that I have with regard to all of this base 12 geometry and the geometry of the dodecagon is that it relates to physics. And we have sort of empty space within the model in the book that I showed you. If you've read the book, you know at the end we get into a grid pattern that is based in units of 0.5 root 2. So that's another thing. All of these triplets can also be presented as in units of square root of 2. You know, if you go this way, you know, there's 3, 1, 2, 3, 4, 5. You still have the right angle in there when you build in units of square root of 2. So there's a lot of things you can do with these Pythagorean triplets that I'm just discovering. I thought it was something interesting and new. So that's Pythagorean triplets. Now I also, when you do this, I also want to introduce you to this idea. When you do this idea of the two circles, when you figure out the radius or the area that's encased or that's defined by these two circles, the area of the ring turns out to be 0.2 pi. So right down here, area equals 0.2 pi, because this radius here is square root of 1.41, and we'd already figured out that the radius of that is square root of 1.21. So you subtract one from the other and you just get 0.2, and pi r squared and all that. So the area of this is 0.2. So now we have the distance between these two rings, one is 0.5 and 0.7. So that distance right there is also just the length of 0.2 on the Cartesian plane. And remember, what's always interesting about the Cartesian plane in base 12 is that a lot of these points just aren't in the same place in base 10. So this is all something that emerges, that's new in base 12. And we got this 0.2 pi in the side of a ring, and this little gap. This is an interesting angle there. And then if we were to draw a circle defined by the point in the middle, which is going to be 0.6, going up here, 0.6. So 0.6 squared in base 12, 6 times 6 looks like 30 or 3 do. So 0.6 squared becomes 0.3. And so the radius of that circle becomes 1.3. I'm going to sort of put it in here. the square root of 1.3. So 1.21, 1.41, 1.3 is right in the middle, or really close. And then we remember also in the book that the radius of that circle is the square root of 1.306. So we have these two circles, the radiuses are very similar. They're only different by 0.006 of area of pi, basically. We're working in units of pi. And that's something else. I'm not that familiar. I'm still learning about math. I don't find a lot of math that relates to sort of radiuses of pi, where you're talking about the thickness, the thickness of circles in units of pi. I'm sure it's out there, but this is what I'm discovering that's all kind of new and different in base 12. So again, it's the decimal places. We're starting in the quantum world, working our way up into the classical universe. I think that journey will have a lot to do with the math of base 12 and in the decimal places, where we're trying to incorporate all that empty space that I talk about in the book, and eventually get to our world where it seems like things are solid, like my book, but ultimately it's full of atoms and molecules and a lot of empty space in there between everything. So a lot of these ideas are presented in my book, Understanding Base 12 Math, How to Draw the Perfect Circle Using Dozenal Geometry. It's available through Amazon. Introduces a lot of new ideas and is the first